students, myself Dr. Bharti Patil. I am your physics teacher for the subject solid state physics. Its code is PH332. From today we are going to start our new chapter, that is chapter 1, the crystalline state. In this chapter we are going to cover the terms related to crystallography. For example, lattice, basis, unit cell, types of unit cell, Bravis lattices, two-dimensional Bravis lattices, three-dimensional Bravis lattices, characteristics of unit cells, then symmetry elements, Miller planes, reciprocal lattices, etc. So let's start our chapter with the introduction. Before going into the actual syllabus, one should know what is matter in order to understand the crystal definitions or the terms related to crystallography. So, what is matter? Matter is nothing but anything that is made up of atoms or molecules. And we know that each and everything in the universe is made up of such type of atoms or molecules. It means it represents matter. There are four different types of matters, and these are solid, liquid, gas and plasma. All these four types are based on the two things, that is interatomic distance and degree of disorder. Let's know what is meant by interatomic distance and degree of disorder. Interatomic distance is nothing but distance between two atoms. Suppose there are two atoms which are separated or very close to each other, then distance between them is called as interatomic distance. And degree of disorder means what? Suppose these atoms are organized or arranged in a periodic manner. It means that they are having order. Suppose there are a number of chairs in a hall and they are sequentially aligned, then we are saying that these are ordered, or there is order arrangement of chairs or the benches in a class. But suppose they are randomly situated anywhere, then we are saying that they are disordered. Similar is the thing in case of representing atoms. If the atoms are ordered, it means that they are periodically arranged, then they are having order arrangement. And if this periodicity is not maintained anyhow, then they are said to be disordered. So, all these solid, liquid, gas and plasma states of matter are based on interatomic distance and degree of disorder. Let's start with solid. In case of solid, the interatomic distance, that is distance between two atoms, is very less. As we move from solid, liquid, gas and plasma, this interatomic distance, that is distance between two atoms, start to increase. It means that as we move from solid to plasma, interatomic distance go on increasing. As the interatomic distance goes on increasing, the degree of disorder also start to increase. Let's see how. In case of solids, there is regular periodic arrangement of atoms because the atoms are tightly bound. As we move from solid to liquid to glass to plasma, gas to plasma, this disorder, that is distance between two atoms, start to increase, and therefore their disorder start to increase. And based on this, as we move from solid to plasma, degree of disorder also increases. In case of solid, interatomic distance is less and degree of disorder is also less. In case of plasma, interatomic distance is more and degree of disorder is also more. Then next, as this chapter is related to crystal structure, we will see what are the solids. We know that solid possesses definite shape and size due to very small interatomic distance and order arrangement of atoms. Again, these solids are classified into two types. These are crystalline solids and amorphous solids. Then what are crystalline solids? In crystalline solids, there is regular periodic arrangement of atoms in a space as shown in figure first. Then what are the amorphous solids? Amorphous solids are the solids in which the interatomic distance is less as compared to liquid, and they are also ordered as compared to liquid, but the atoms are randomly situated as shown in figure. The examples of crystalline state are the metal atoms. Then amorphous are glass, then wood. Let's differentiate or find the difference between crystalline solids and amorphous solids. So, let's start with the definition. In case of crystalline solids, there is regular periodic arrangement of atoms or molecules in a space, and such type of periodic arrangement is missing or not present in case of amorphous solids. Then this crystalline solid possesses internal spatial symmetry. These are symmetry of atomic orientation, and hence if we try to break them, they start to break in a regular shape. But as amorphous solids are not having periodicity of atomic arrangement, if we start to break them, they will break into the pieces of irregular shape. Then they have directional. Crystalline solids have directional properties. It means that their physical properties will remain same along a particular direction, and this phenomena is called as anisotropic substances. What are the amorphous solids? Amorphous solids don't show any such directional property, and hence they are called as isotropic substances. Their properties will differ in different directions because there is no any periodicity of atomic arrangements. Examples of crystalline solids are silver, gold, copper and silicon. Examples of amorphous solids are glass, plastic, rubber and wood. Now let's have definition of crystallography. What is crystallography? Crystallography is a branch of physics or material science which deals with the study of geometric forms and other physical properties of crystalline solids with the help of tools such as X-rays, electron beams and neutron beams. That is, crystallography is a branch of solids which deals with study of various forms of crystals and their properties. Then, in order to understand the crystallography, we should learn few of the terms related to crystallography. First one is space lattice. What is space lattice? Space lattice is nothing but regular periodic arrangement of atoms in three-dimensional space so that each point will have same environment as that of other. It means that there is regular periodic arrangement of atoms in three-dimensional space, and the environment about each atom will remain same. Such type of arrangement of atoms is called as points is called as space lattice. So next point is lattice points. Lattice points means what? Suppose I want to draw a rangoli, then how I will start to draw? I will put few points at regular interval of time. It means that each point that I have drawn will represent a lattice point. If I continue to draw such lattice points in two-dimensional space, then it will give us two-dimensional structure or the two-dimensional arrangement of points. And if I draw in 3D, then along x, y, z axis, then it will give me a three-dimensional space lattice. So Lattice points are nothing but the points which we have drawn in a space. So there are two types of space lattices, two-dimensional space lattice and three-dimensional space lattice. Suppose we consider only two axes, that is x and y axis, then the whole crystal structure can be drawn with the repetition of a, that is distance between two points along x-axis, and distance between two atoms or points along y-axis. If we start to repeat this, the whole entire structure will be built up. And this diagram shows a resultant vector. So a translational vector in case of two-dimensional space lattice is given by n1 times A plus n2 times B. A is nothing but length or interatomic distance along A, that is x, and B is nothing but interatomic distance along y-axis, and we have considered only two axes, and we will build entire structure by repeating A n1 times and B n2 times. The whole structure can be built up. This is called as two-dimensional space lattice. In case of three-dimensional space lattice, we have to consider three axes, that is x, y and z axis, and the whole crystal structure can be drawn by repeating A n1 times along x-axis, B n2 times along y-axis, and C n3 times along z-axis, where n1, n2 and n3 are the integers. Hence, translational vector in three-dimensional lattice is given by n1 times A plus n2 times B plus n3 times C. Now, what is basis and what is crystal structure? Suppose I want to draw a crystal structure of copper. Then I have to place, as I want to have a solid structure, I have to place the atoms in periodic way. Then how to maintain the periodicity? In order to maintain the periodicity, one should have the location where I have to place the copper atoms. So initially we have to draw a lattice or consider a lattice. It is nothing but the arrangement of points at regular intervals, and to that we have to attach copper atoms. It means the arrangement of points will have a crystal lattice, and the atom of copper that we are going to place is called as basis, and this lattice plus basis is going to give us crystal structure of copper. Hence, lattice plus basis gives us crystal structure. So what is basis? Basis is nothing but group of atoms or molecules attached at each lattice points, and same is shown in this figure. Crystal lattice is shown by regular periodic arrangement of atoms. To that each point we have to arrange a basis. So lattice and basis, that is group of atoms or molecules attached at each lattice point, is going to give us crystal structure. So friends, today we have started our syllabus with the introductory part related to the crystalline state from chapter 1, and in that we have covered the points such as what is matter, what are these states of matter, then how they are classified on the basis of interatomic distance and degree of disorder, what is the importance of these two terms, then what is solid, what are the types of solids, what is difference between crystalline and amorphous solids, what are the examples of crystalline and amorphous solids, then what is crystallography, what are the terms related to crystallography such as space lattice, lattice points, two-dimensional space lattice and three-dimensional space lattices, their translational vectors, then what is basis and how to build a crystal structure with the help of lattice points and bases. Hope you have enjoyed today's lecture. Thank you.